All right, so we've got these two masses, or these two beetles, P and Q, hanging either side of a vertical cylinder, right? So it tells you their masses in terms of m. Um, they're connected by spider silk. Okay, all right, light inextensible string. What we can take from that is the string has no mass and doesn't stretch. It keeps a fixed length, and the length is pi over 2. Pi over 2, what does that really mean? Well, we know that the cylinder has a radius a, so the circumference of that is 2 pi a, yeah? Which means that this pi a over 2, that's like a quarter of the circumference. So these two masses are connected by like 90 degrees apart. Right, let me draw this diagram for you. So that's like the key part of this question. If you can draw the diagram, then there's just two ideas you need to know. How to resolve forces using F equals ma, and how to use, there's another trick, conservation of energy, which is something I keep forgetting to do. That's the other thing you want to use to solve this question. Right, let's draw this diagram. So we have P 3m and Q 4m. So if you think about it, the 3m is going to be, the 4m is going to be higher than the 3m, isn't it? Okay, I'm gonna draw it like this. So we'll have, that's Q, our 4m mass, and over here we're going to have P. Let me change the brush width a bit. And over here, we're going to have the center of the circle. All right, remember Q is 4m and P is 3m. And then this, let's draw on a couple of forces. Let's draw on, there's gravity acting on Q there, 4mg. And gravity acting on P as well there, so that's 3mg. Obviously both going straight down. And they're supposed to be connected by this string, which is of length at pi over 2. And what that really means is that there is 90-degree angle there. Right? What are the forces that we're missing? Simply just the reactions. We won't really be considering them in this question, actually. You'll see in a second. But it's good to have them in the diagram. What else? We have tension acting tangentially to each guy here, like that. Okay. Now, if this system's in equilibrium, what can we say? We can say a couple of things. Like nothing's moving, so up equals down and whatnot. Screenshot here. Let's go to this question again. Where is theta? So theta is between OQ and the vertical. Let's just be careful to get that right in our diagram here. So here's the vertical. What color should I use for theta? I will use sort of a dark blue. How about that? So there's our angle, theta. Okay. Now if you think about this for a minute, you'll see that theta must also be here, right? I'm sure you can convince yourself of that if you're doing this kind of problem. Right, let's show that tan theta is 3/4, 3/4. How do we do that? Well, what we want to consider is the fact that none of these beetles, none of these, P or Q, are moving tangentially to the circle, right? So if you consider this force here, if I resolve the weight, remember that theta is also here, so if I resolve this weight, it's 4mg going to be sine theta. This must equal the tension because it's not moving side to side tangentially, right? And similarly, if we resolve the tension also this way, not the tension, sorry, the weight that way, because the theta is there as well, you're going to have 3mg cos theta. That's also equal to the tension. right? Because it's not moving. Well, if they're both equal to the tension, then they equal each other. So we have 4mg sine theta is equal to 3mg cos theta. Okay, we can just cancel the mg there. And what else can we do? We can divide by cos theta and divide by 4. Right? Remember, sine over cos is tan. And let me move that 4 over here. So then you just get your result immediately. Tan theta equals 3/4. That's really it. There you go. That's all that's happening. Okay, so that's the first part of the question done. Okay, B, so, they're moving slightly now. Right? A gust of wind disturbs the point in the middle, and now they're sliding downwards. Okay, so while they're still in contact with a pipe, we want to show that the angle theta satisfies this equation here. Now, if you look at it, it looks kind of daunting, like what are all these terms? Well, if you think about it, this looks a bit like kinetic energy, doesn't it? You'll see that in a minute. This could be, if I times it by another unit, this could be, what is it called? Gravitational potential energy. So really, you just get this equation by doing conservation of energy. So let's work out how to do conservation of energy. How would I actually do conservation of energy for this problem? Well, let me just draw it again for you. So draw the circle. And this time they're moving, but we're still going to be considering theta in the same way. So here's Q, here's P, 90 degrees apart, here's O. Let's work out the gravitational potential energy of these guys. To do that, I need to sort of take a relative origin, a relative zero for my GPE. So I'm just going to do that through the center of the circle. Right? I'm just going to say that the gravitational potential energy is 0 here. Right? Now remember, what is gravitational potential energy? It's mass times g, the gravitational constant, times height, mgh. So really the only tricky thing, because I already know the masses of these guys, the only tricky thing is that I want to work out the height of them. Remember, theta is still kind of here, although it's moving. Remember, the radius is a. So what is the height of Q above O? Well, trigonometry just says that this is a cos theta. Okay, remember theta is also here, and you can see that the height of P is a sine theta. All right, so what's the total GPE? So the total GPE is 4, so the mass times the gravitational constant times the height, cos theta. So that's the GPE of Q. What's the GPE of P? So that's going to be mass of P, 3m, times gravitational constant times the height of P, again above this GPE 0. Okay. Now, what's their kinetic energy? So there's two kinds of energy these guys have. It's going to be gravitational potential energy, right? And then kinetic energy. So we're also going to have kinetic energy of both of them. Now, if you remember your circular motion equations, the tangential speed I can write as a theta dot, right? So a half mv squared is the kinetic energy. So that's going to be a half ma squared theta dot squared. Right, so what's the ke of Q? It's going to be, so a half times the mass, 4m, times a squared theta dot squared. Then we're also going to have the ke of P. Okay, now this is conserved, so it's always equal to a constant. But what is that constant? Well, if you think about it, back here, we can use this, right? So at the start, they weren't moving, so they had no kinetic energy. The only energy in the system of beetles was gravitational potential energy. And we know the gravitational potential energy is 4 mga cos theta plus 3 mga sin theta, right? But we know the value of theta when they are in equilibrium is tan theta is 3/4. Okay, and I'm going to most usefully use that information like this, right? So my 5 up here. So I know that sine theta is 3/5, and I know that cos theta is 4/5. So I'm going to be using those to work out what this constant is. Now remember, the gravitational potential energy is 4 mga cos theta plus 3 mga sine theta. So that's 4 mga cos theta, so 4/5, plus 3 mga times 3/5. Okay, so what's that? That's going to be 25/5 mga. You know, or 5 mga. So that's the energy at the start. The energy at the start is 5 mga. Right, now conservation of energy says that, the energy in the system is conserved, so even though when theta is changing, this must be equal, this guy up here must be equal to 5 mga. And you can see that this is basically this equation here, the 7a theta dot squared plus, ag cos theta, right? Why is it the same? Well, because all I need to do is tidy it up a bit of algebra. You can see that I can cancel an A, and I can bring the masses together, the kinetic energies together for this bit, and I'll leave it for you to tidy up, and you'll get exactly that equation there. Okay, you'll get B. So that's B done. Just conservation of energy. That's all we need to do. Remember, you can take your dp to be 0 anywhere, and it makes sense to take it in the middle of the circle, right? That's the most sensible place to take it, because then you can get nice expressions for the height of these two particles. So that's what we've done. All right, last bit of the question wants us to consider when Quentin loses contact with the pipe. Okay, how does that look different from when they are in contact with the surface? Well, what that's gonna look like is Quentin will basically, okay, so if he loses contact with a pipe first, what the next state of our system is going to look like is that he has moved downwards, so he's going to be like here, right? It's going to look something like this. Remember, Quentin's Q, this is P. So he loses contact with a pipe first. He's going to come off the pipe. Now mathematically, or physically, what that means is that NQ, right, the normal reaction here, is equal to 0. So we want to find when that's true. When is it equal to 0? Now you need to remember that when you have Q in this sort of scenario, what we're going to have is, okay, well, we have Q here. We're going to consider the centripetal acceleration. It's going to be a theta dot squared. And we know that the force inwards is 4 mg cos theta. And we have this normal reaction here. else. Nope. So it's like this. Let's use our F equals m to do the equation of motion here. So 4mg cos theta minus nq is equal to 4m, so mass times acceleration. Okay. Now this is going to be our equation 1. And we want to show that when this is true, theta is basically equal to b. So I'm going to be combining this with what we've discovered for equation 2. So that's 7a theta dot squared plus 8g cos theta. Okay. Write that down here. So we know that plus 6g sine theta equals 10g. Okay. Now we want to say that, look at equation 1, when nq equals 0, we're at that angle beta. That's the beta in question. So we have 4mg cos beta equals 4m a beta dot squared. Let's cancel the m's. Okay, so it's pretty similar to this. I'd like to substitute out the 7a dot theta, a theta dot squared, so I can just see that that's equal to 7, isn't it? Yeah, you can cancel the 4's and just replace them with 7's. And then we're done, right? Because then you know that this guy is just going to be 7 cos beta, right? And you add that already to the 8g cos beta, or 7g cos beta. So we get 15g cos beta plus 6g sine beta equals 10g. Okay, so let's go over that one more time. How did I do that? So 1, you just remember the formula for the radial acceleration, right? Then 4mg cos theta minus the normal reaction. That's just F equals ma. Equation 1 is just F equals ma applied radially. And we know that it said that when theta equals beta, Quinta loses contact with a pipe. So we know that when theta equals beta, okay, when theta equals beta, it means that this guy's true. nq equals 0. So we plug that into this radial F equals ma equation. And we see that for all values of beta, we sort of have like, g cos beta equals a beta dot squared. Then I can use my equation 2, the result I already have. I just replace the beta dot squared with the cos beta, and then I'm done. Then I get this lovely relationship here: 15 cos beta plus 6g sine beta equals 10g. In other words, I can basically find beta in terms of g. So I know my beta exactly. Right? So that is that.